Hello, what's up, everybody? This is Teacher France once again, and in this video, you will be learning one of the topics in Math 3 or pre-calculus, which is the mathematical induction. To start with, Giovanni Vacca of 1872 to 1953, who is an Italian mathematician who introduced mathematical induction during those years. And moving forward, by definition, or what is a mathematical induction? Mathematical induction is a mathematical technique which is used to prove a statement, a formula, or a theorem is true for every natural number. A theorem provable by complete induction involves a statement about an integer, usually denoted by n, which is to be proved for all values of an integer. There will be two parts in proving. The first part improves that the first part proves that the theorem is true in a special case, that it is for a special value of the integer n involved in the theorem. The second part of the proof is what has been called an argument from n to n plus 1. How do we do it, or how to do it? Step one is we consider an initial value for which the statement is true, or shall we say proving the statement is true for n is equal to 1. For step two, we evaluate the statement for n is equal to k. And lastly, we prove the statement is true for n is equal to k plus 1. In other authors or in other books, they only have two steps. Step 2 and step 3 can be combined together into step 2 alone. But here in the definition, we could have step 2 to step 3. In my case also, I prefer to write step 1 and step 2 together only, like combining step 2 and step 3. But it is still on your part whether where you wanted to feel comfortable. If you wanted to have until step 3, that's okay. But if you wanted to have until step 2 where you combine the step 2 and step 3 here, that is also okay. Let us start with our first example here. We have proved by mathematical induction, or MI, that 1 plus 2 plus 3 plus and so on plus n is equal to 1/2 n times n plus 1. All right. And I have shown you there earlier the steps that we will be working on. But before that, for us not to be confused, what I will be doing is to rewrite our, we will be rewriting our original statement. As you can see here, you might be confused that there is a 1/2 here, which means how do we deal with that 1/2 there, sir? In dealing with the 1/2 there, we will just simply rewriting everything from the left side of our equation. Okay, in rewriting there the equation, it will become 1 plus 2 plus 3 plus and so on plus n is equal to n times n plus 1 all over 2. I rewrite it here because it's easier for us to work on the statement or to work on the given we have. Let us start with step 1. Okay. For step 1, it is what we call the basis. How do we work on the basis? So for step 1, we are going to let n be equal to 1, which means in our left side here, we have the value n. We are going to substitute n be equal to 1. And as you can see here in our first term, we already have when n is equal to 1, the answer is 1 for the series. And we need to prove it from the left side going to the right side if they are equal. So we have n here on our left side, which is the first term. When n is equal to 1, the answer is 1. On the right side, we substitute there the value 1. As you can see, this is our right side of our equation. We substitute the value 1 there. And that will become 1 times 1 plus 1 all over 2. Therefore, 1 is equal to, let us combine what we have here on the right side. That is 1 times 2 over 2. 1 is equal to 2 over 2. Therefore, 1 is equal to 1. And this is true for n is equal to 1. And after that, we proceed with our step 2. I'll be writing here our step 2. Step 2 states that we assume, this is an assumption where n is equal to k, which means we substitute k to the variable n here in our original given. Therefore, it will become, the given will become 1 plus 2 plus 3 plus so on plus n, which is equal to 1/2. I forgot to change the n. It should be k already. All the n variable will become k. So it should be k here. K, then 1/2 k times k plus 1. Or you can have k, quantity k plus 1 over 2. And this is an assumption, and this assumption will be applied in our proving. So we could also rewrite it there for us not to be confused. For the denominator 2 plus k, which is equal to k times k plus 1 all over 2. Okay, so that is the step 2 there. Moving forward, we will have step 3, which is proving when n is equal to k plus 1. So here in our step 3, we are going to show that it is true or show true for n is equal to k plus 1. Therefore, when n is equal to k plus 1, it should be 1 plus 2 plus 3 plus and so on plus k plus 1, which is equal to k plus 1 quantity k plus 1 plus 1 all over 2. Okay, in step 3, guys, you must not be confused. Why did we add k plus 1 there? Because the k here already existed. And then, remember that we have a value n. So it should be 1 plus 2 plus 3 plus and so on plus k plus n. Therefore, the n there will be changed to k plus 1. And then for the right side, we simply rewrite the n into k plus 1. And you can see it there, the changes. For us not to be confused, you need to operate here the k plus 1 plus 1. It will become k plus 2. And then we will work on with the proving. So this is the start of our proving. Moving forward, we will have 1 plus 2 plus 3 plus k plus 1 which is equal to k plus 1 quantity k plus 2 all over 2. I forgot to write here the and so on and so forth. So there should be and so on and so forth plus k plus k plus 1. Okay? And then after that, as you can see in our step 2, in our assumption, we are going to substitute our assumption. This assumption in step 2 here is very important because this will help us in our proving. As you can see, the assumption existed on this part, which means this part of our given will change into k times k plus 1 all over 2 plus k plus 1, which is equal to k plus 1 times k plus 2 all over 2. Alright, so we're almost done with our proving for step 3. As you can see it here, that the next step will be combining our terms. We have a denominator 2 here, and we have a denominator 1 there. So for the next step, we will be finding their least common denominator, then we combine both numerators afterward. For us not to be confused, I will be erasing now the first part here so that we will be guided. Or we could proceed with the next page. Okay, don't forget this last part there. We will be combining, or allow me to rewrite it here on the next part. Okay, on the next part, the remaining values are k times k plus 1 k times k plus 1 all over 2 plus k plus 1, which is equal to k, it's k plus 1 times k plus 2. For a moment, let me erase this. Okay, it is k plus 1 times k plus 2 there. K plus 1, k plus 2, all over 2. Okay, don't forget to write there all over 2. Our goal there, the left side and the right side of the equation should be equal, which means that finding the LCD here, we will have a denominator or LCD which is 2 for both terms. And then we do the process, 2 divided by 2, that's 1, and then we copy the numerator on this part. k plus 1 plus, since the denominator here is 1, 2 divided by 1 is 2, so it's going to be 2 times k plus 1 there. Before we do the combining part. Afterwards, we will be working on the left side. How are we going to combine all of them? Remember that our goal is to become k plus 1 times k plus 2 all over 2. Alright, allow me to write it first. Here, our left side, k plus 1 times k plus 2 all over 2. Okay, the idea there is to look at our left side carefully. This is the first term, this is the second term. As you can see, we can factor out, we can do common factoring by looking their common factors. So as you can see in this part here on the left side, the common factor will be k plus 1, which means we factor out k plus 1 outside, And then the remaining values, the k and the 2 there, will still remain, and that is k plus 2 all over 2, and this is equal to k plus 1 times k plus 2 all over 2. And now we have proven when n is equal to k plus 1, the left and the right side is also equal. And then for your last statement, it should be therefore or thus. For the given, you write here by PMI. It's not B, but it's P. It should be P there. Thus, by PMI or by principle of mathematical induction, then you rewrite again the given. The given 1 plus 2 plus 3 plus and so on plus n is equal to n quantity n plus 1 all over 2 for all positive integers and that should be the final statement that we will be looking for after completing our step 3. Let us now move forward to our another example. Prove by mathematical induction. Allow me to read that. Prove by mathematical induction that 1 squared plus 2 squared plus 3 squared plus and so on and so forth plus n squared is equal to the n quantity n plus 1 times the quantity 2n plus 1 all over 6. Then we will have the same step to follow for this case. Let us start with step 1 when n is equal to 1. As you can see here, the series or the pattern of this series is through n squared. When n is equal to 1, 1 squared is 1. When n is equal to 2, 2 squared, that's 4, and so on and so forth. That's the pattern for the series. Therefore, we need to start with the step 1. I'm going to write here the step 1. Okay, for a moment, this will be step 1 here. Step 1 will be proving when n is equal to 1. As you can see it there, we have it here, n squared. So we will substitute 1 there. So that's going to be 1 squared is equal to, substitute also 1 to all the variable n. That will become 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. Therefore, the left side is 1 is equal to 1 times 2 times 3. Why is it 3? That's 2 times 1, 2. 2 plus 1 is 3. Here, 1 plus 1 is 2. Then times 1. So you can see it there on the numerator. Then all over 6. Therefore, we simplify. 1 is equal to 1 times 2 times 3. That is 6 all over 6. Then 1 is equal to 1. So this is correct. That's for the step 1. For step 2, we are going to assume or we let n be equal to k. We will be rewriting or we will be substituting k to all the variables n on our given. That's 1 squared plus 2 squared plus 3 squared plus and so on plus k squared, which is equal to, let me erase it first, this one, which is equal to k times k plus 1 times 2k plus 1 all over 6. And then we will be applying the assumption here to our next step. We are now proceeding to step 3. And in our step 3, it will be showing, or we will show, or we will prove that it's gonna be true for n is equal to k plus 1, which means we are going to substitute k plus 1 to our variable n in the original given. And that will become 1 squared plus 2 squared plus 3 squared plus and so on plus k squared plus k plus 1 squared. Okay, don't forget there should be k plus 1 squared, which is equal to, that will become k plus 1 times k plus 1 plus 1, then 2 times k plus 1 plus 1 all over 6. So that's for the right side. Okay, again, remember that k squared existed. We will not change k squared. It's still part of our series. Then, as we all know, there will be plus n here. And then the n there is k plus 1. And then the pattern is n squared. Take note that it's n squared. Therefore, it's going to be k plus 1 squared for the pattern of the series. And then we are going to simplify the right side. We copy the left side of our equation. 1 squared plus 2 squared plus 3 squared plus so on and so forth plus k squared plus k plus 1 squared, which is equal to, simplify everything on the right. That's k plus 1 times k plus 2, because k plus 1, we can only add there the constant values. Then that's gonna be 2k plus 2. We are going to distribute that 2k plus 2. Then we are going to combine 2 and 1. That will become 2k plus 3 all over 6. And then we are now going to substitute or make use of our assumption in step 2 that this is equal to k times k plus 1 times 2k plus 1 all over 6 plus k plus 1 quantity squared, which is equal to k plus 1 times k plus 2 times 2k plus 3 all over 6. All right, we're almost done there because our goal is to make the left side and then the right side be equal. Okay, our goal here is to find first their LCD. It's very easy. We have 6 and 1 for the denominator, therefore the LCD is 6. And then we copy the first term here, that's k times k plus 1 times 2k plus 1 plus 6 times k plus 1 quantity squared. How it become like that? Remember the process. 6 divided by 1 on the denominator is equal to 6. Then you times the numerator. So that's 6 times k plus 1 quantity squared, which is equal to k plus 1 times k plus 2 times 2k plus 3. This will be the phase of the goal. This will be the goal that the left side should become the same with the right side. Now we will manipulate what's on our left side. As you can see here, we can factor, or we could find a common factor on this part, which is the first term, on the first term of our numerator, we have k plus 1. And then on the second term, we have k plus 1 squared, which means we can factor only k plus 1 alone. Just the same thing we did from the last example that we were factoring. So here, we factor k plus 1, and we are going to rewrite the remaining value. So we have here k times 2k plus 1 plus 6 times k plus 1 alone. Only k plus 1, as you can see, it's squared. But we factor out 1k plus 1 outside. Therefore, the remaining value for k plus 1 squared will be k plus 1 alone. Then don't forget, it's all over 6. And here, this is k plus 1, then k plus 2 times 2k plus 3. And this is also all over 6. And then we are going to simplify that. We don't have enough space. We are going to proceed to the next part. I'm going to rewrite this last here on the next slide so that we will be guided accordingly. So we have it here, k plus 1. We were factoring earlier, right? So let me rewrite here, k times 2k plus 1, then plus 6 times k plus 1. This is the left side, all over 6. Then for the right side, that is k plus 1 times k plus 2 times 2k plus 3, all over 6 also. Okay, now we proceed here from the left side. We are going to um, simplify inside the bracket first. As you can see there, we simply distribute this one, and then we also distribute this one before we combine them. Then that will become, rewrite k plus 1, then let us work on with the bracket. That's 2k squared plus k plus 6k plus 6 all over 6. Okay, then this is equal to k plus 1. We are going to simply write it the same way. 2k plus 3 all over 6. Now we can combine here inside the bracket. That will become k plus 1, and then inside the bracket that will be 2k squared. We combine k and 6k plus 7k plus 6 all over, okay, I'm sorry for the line, that's all over 6 is equal to k plus 1 times k plus 2 times 2k plus 3, which is all over 6. All right, I think we have an idea already that in this trinomial, we can still factor out the given trinomial. 2k squared plus 7k plus 6, we can make it into two factors by simply k plus 1 times k plus 2 times, this is 2k plus 3. Okay, sir, how did you know that the factor for 2k squared plus 7k plus 6? The only guide there is you're going to look at the third term, which is 6, and then what are factors of 6? 2 and 3 are factors of 6. How about here, the middle term is 7. You need to find a way whether the 2k is either in the plus 2 or in the plus 3. But in my idea, or in my case, it should be in the plus 3, 2k plus 3, because When finding the middle term 7k, that is the inner, right? This is 4k, and then this is 3k. Therefore, 4k plus 3k is 7k. That's how I do that. And then k times 2k is equal to 2k squared. So they are just equal there above. And then we have now proven that the left side and the right side are just equal. K plus 2 times 2k plus 3 all over 6. And then for the last answer, therefore the given 1 squared plus 2 squared plus 3 squared plus so on plus n squared is just equal to the n quantity n plus 1 times 2n plus 1 all over 2 for all positive integers. For all positive integers. And okay, so this will be the final answer for that example. Simple as that. All right. And don't forget that it's by um, principle of mathematical induction. Okay, I forgot to write there the by PMI, or you can write it here on the last part for all positive integers by principle of mathematical induction. Or by principle mathematical induction, you write the given. This is true. Forget to write is true. Therefore, the given is true for all positive integers and by principle of mathematical induction. Or you could have, therefore, by principle of mathematical induction, then you write the whole given is true for all positive integers. And that's how you end your proof. And don't forget to write here the box, shaded box up. This will signify that you are done with the proof. Or if you don't feel like doing this, but this is for technicality purposes, you write the shaded box on the last part. And also with the first given that we had, we need to write there the box shaded as a proof that we're done, or this is the end of the proof. Or you can simply state it end of the proof. That's how the shaded box is all about. Let us move forward with our example number 3. Prove by mathematical induction that 1 times 3 plus 2 times 4 plus 3 times 5 plus and so on, and that there should be plus n times n plus 2 is equal to n times n plus 1 times 2n plus 7 all over 6. And again, we are going to follow the same steps, starting with our step 1. We are going to, for step 1, we let n be equal to 1. As you can see here, where is n on the left side? N is here. This is the pattern for the series. That when n is equal to 1, the answer here is 1 times 3. This is the n actually. N, and then that's times n plus 2. Remember, when we say n plus 2, that's 1 plus 2, that's times 3. That's the pattern all about. Same goes here, that n times 3 is this one. This when n is 2, that's times 4 because that's 2 plus 2. You need to understand the pattern all about. This is the pattern for each term. The pattern of the series for each term, the n times n plus 2. And that is true for all the terms there in this given. Now let us substitute n equal to 1. So that will become 1 times 1 plus 2 which is equal to 1 times 1 plus 1 times 2 times 1 plus 7 all over 6. And this is 1 times 3. That is 3 here, which is equal to 1 times 2. That's 2. 1 plus 1 is 2 times 2 plus 7 is 9 all over 6. Then we simplify. 1 times 2 is 2. 2 times 9 is 18 all over 6. 18 divided by 6 is equal to 3. Therefore, it is true for step 1. Step Step 2 is the assumption. We are going to assume, we will be assuming n be equal to k, which means that we are going to substitute n with the variable k. That's 1 times 3 plus 2 times 4 plus 3 times 5 plus so on plus k times k plus 2, which is equal to k times k plus 1 times 2k plus 7 all over 6. So that's for step 2. Moving forward with step 3. For step 3, we are going to show that it is true for n be equal to k plus 1. So we start with the given, and then don't forget that we already added in our series the k times k plus 2. We need to include that. Then we need to add plus n. Then that should be plus k plus 1 more. So starting with the given, that's 1 times 3 plus 2 times 4 plus 3 times 5 plus and so on plus k times k plus 2. Then we are going to add plus n, which is k plus 1 plus k plus 1 times, look at the pattern, that's k plus 2, which means this is k plus 3 for the left side. And then we don't have space now for our right side. So for the right side here, I'm gonna write it here below, which is equal to, okay, the space here, I'm gonna write it here below, so don't be confused. That is the right side of the equation. That's gonna be k plus 1 times k plus 1 plus 1, then 2 times k plus 1 plus 7 all over 6. So this is the right side of the equation here in our step 3. So don't be confused in my writing there. After that, we are now going to change this one with our step 2 we had, that this is equal to, so that we will have smaller space to consume. We are going to apply the assumption that it's going to be k times k plus 1 times 2k plus 7 all over 6 plus, don't forget that we added there k plus 1 times k plus 3. Based from the pattern, and this is equal to, let us simplify the right side, k plus 1 times k plus 2 times, this is going to be distribute 2 there, that's 2k plus 2, then 2 plus 7 is 9, so it's going to be 2k plus 9. 2k plus 9 all over 6. Okay, so we already have the idea there on how are we going to make left side and then the right side be equal. We are going to work on with the same process that on the left side there will be an LCD 6, so there both the denominators will become 6, then 6 divided by 6, therefore we copy the first term, k plus 1, because 6 divided by 6 is 1 times the numerator, we just copy the numerator, 2k plus 7. And then here we have an invisible denominator, 1. 6 divided by 1 is 6 times the numerator, so we're going to times 6 in the numerator. That will become plus 6 times k plus 1 times k plus 3, which is equal to, you copy everything on the right side, k plus 1 times k plus 2 times 2k plus 9. That's on the right side, all over 6. Therefore, we are going to simplify and then work on with the right side. As you can see the two terms in the numerator, we can look for a common factor, which is just the same. K plus 1 can be factored out here. That will become k plus 1 outside. Don't forget that this is separated by this line. K plus 1 is being factored outside, then the remaining values for the first term can make use of a bracket. That's k times 2k plus 7. And then after that, plus 6 times k plus 3. All over 6. This is 6. Which is equal to, you copy everything on the right, k plus 1 times k plus 2 times 2k plus 9, all over 6 also. Afterwards is to combine on the inside the bracket. So you are going to simply distribute that, and then combine afterwards. I think we don't have space here. We will be proceeding with the next slide. And I'll just copy the remaining or the last part here. So that's gonna be k plus 1 here. Then there's a bracket for that. That's k 2k plus 7, then plus 6 times, it's k plus 3, then close bracket, all over 6, which is equal to, that's k plus 1 times k plus 2, then 2k plus 9, all over 6, which will be the goal of our left side. So again, going back, we are going to distribute, and then combine afterwards. Copy k plus 1, then k times 2k is 2k squared. K times 7 is equal to 7k, plus 6 times k is 6k, 6 times 3 is 18, all over 6. And then you copy the right side, k plus 1, then k plus 2, 2k plus 9. There you go, all over 6. Then we combined here 2k squared plus 7k plus 6k plus 18. That will become k plus 1 times 2k squared plus, that is 13k, 13k plus 18. All right. Then this is all over, this is all over 6. We're almost done. and then you copy again the right side. K plus 2 and 2k plus 9. I think you already have the idea what is the factor for that trinomial there. 2k squared plus 13k plus 18. You can still factor them into two factors. That is k plus 1. You bring down k plus 1. Then the two factor will be, the guide will be from the right side. And let's double check if it's correct. K plus 2 times 2k plus 9. How do we double check? First is the middle term 13k. That's, we are going to add the values of this one. 9k, that's k times 9 is 9k. 2 times 2k is 4k. 9k plus 4k is equal to 13k, so that is correct for the middle term. 2 times 9 for both last terms is 18. K times 2k is 2k squared. Therefore, this factor we had is correct. And now, this is already equal to our right side, which was our goal. 2k plus 9 all over 6. We have it here, all over 6. As you can see, we have now equal from the left and then from the right. Therefore, or you can have thus, by principle of mathematical induction or by mathematical induction, um, it is true, or you write the given, which is 1 times 3 plus 2 times 4 plus 3 times 5 plus and so on plus n times n plus 2, which is equal to n times n plus 1 times 2n plus 7 all over 6 is true for all positive integers. Okay, and that's how you're gonna work on um, given, and or let us say this is how you're gonna prove a certain statement by principle of mathematical induction. It's gonna be quite lengthy on working on, but the main thing that I'm gonna give you, or the advice that I could give you, is that you need to be patient in working on the steps. Like you do it step by step. But if you wanted to do some shortcuts, like sir, I wanted to do things like this into shorter way, then it's up to you to find some shorter way on the step. As long as we are going to arrive with the same answer that we will be proving on the last step, where showing the n be equal to k plus 1, where the left and the right side be equal. And that should be the last goal. And then you need to end up with our last statement. And don't forget to write there the box, then shade it, which signifies that it is the end of our proof. Thank you so much, everyone, for tuning in with me on how to work on the principle of mathematical induction, or solving that's a series or an equation with a series through principle of mathematical induction. Have a great day ahead.